Alright, so in this video we're going to break down this simple basic tutorial sheet on intermolecular forces and phase diagrams. Okay, question 1. Soaps and detergents contain surfactants, the surface active agents that disrupt the intermolecular forces in order to allow its spreadability. What intermolecular forces are disrupted in water by surfactants? So these are the questions that we're going to answer in this video. So you can see phase diagrams are part of the questions that we're going to answer. Okay, so altogether we're going to answer 8 questions. Okay, let's start with the very first one. Soaps and detergents, they contain surfactants. These are surface active agents that disrupt the intermolecular forces in order to allow its spreadability. What intermolecular forces are disrupted in water by surfactants? So this question is just basically very simple. It just requires you to be able to identify the intermolecular forces that are present in water. Now, if you've watched the videos on the side where I've explained about the intermolecular forces, you understand that water is made up of 2 intermolecular forces, actually 3 intermolecular forces. The strongest, which are the hydrogen bonds, okay? And then we understand that water is actually a polar molecule, right? So it also contains dipole to dipole interactions, okay? Dipole to dipole interactions. You understand that dipole to dipole interactions occurs in polar substances. So if I was to draw water like this, okay, so these ones I've drawn with lines. In fact, let me just do this. Let me bring you here and then you can see clear what I'm talking about. So if we're to have water like this, the ones I've drawn with lines, these are called intramolecular forces. Now the intermolecular forces, we tend to draw them using dots. So let's have another water molecule just down there. So this will be oxygen and then hydrogen, like that. So again, you see that this is again connected to another water molecule in the similar manner, okay? And then the oxygen as well is attached to other hydrogens in other water molecules. Okay, so the basic idea is in this case we know that hydrogen is going to be partially positive because water is polar. Okay, so is the presence of the partial negative charges on the oxygen and the partial positive charges on the hydrogens. So these ones will be attracting with the opposites on the other molecules of water. So these are what we now call the dipole to dipole interactions. Okay, so now the specific some specific or special dipole to dipole interactions are what we call hydrogen bonding. Okay, so the specificities of hydrogen bonding, hydrogen connected to oxygen, hydrogen connected to nitrogen, hydrogen connected to fluorine. So in this case, these are going to be special hydrogen bonds. So I think you get the answer now, right? So therefore, what intermolecular forces are disrupted in water by surfactants? The simple basic answer is hydrogen bonds. Okay, so hydrogen bonds and in general dipole to dipole interactions. Okay, question 2. The diagram below shows the effect of intermolecular forces on the boiling point of different molecules made from atoms in the same period and groups on the periodic table. Explain the observed trend in the boiling point of molecules made from group 4 and group 6 atoms in the diagram below. Okay, so these elements are from the same period and they are categorized again to the groups that they're in. Now we have to explain the observed trend in the boiling point of molecules made from group 4 and 6. So let's try to observe what's happening. This is group 6 to start with. So we'll see that we've got water. So the hydrogen is just basically attached to everything, right? So oxygen, sulfur, and the rest. Okay, so that's group 6. These are group 6 elements. Oxygen is of course on top if you go to group 6. Okay, so now the question here is, why is it that the boiling point of water is 100, and then when you go down the group as you get to sulfur it reduces, and then from sulfur going up it begins to again increase? Why is it so? Again, if you observe group 7, hydrogen fluoride as well has got a higher boiling point, reduces as you go to HCl, and then again begins increasing. This is the trend that we are observing. Okay, now for the other one, group 4, it has started actually, as you start from carbon going down, what's happening is that what? They are just increasing. Okay, so this requires your understanding of the intermolecular forces for you to be able to explain this trend that we are seeing. So I've already given you a hint of where hydrogen bonds occur. So hydrogen bonds, I've already mentioned, they occur between hydrogen and oxygen, and then hydrogen and nitrogen, hydrogen and fluorine. So you already have an idea, right? So therefore water, due to hydrogen bonds, that's why we are seeing that. That's why they are higher. That's why we've got higher boiling points. These ones, they've got higher boiling points because they contain hydrogen bonds, including this guy, because of the presence of what? The hydrogen bonds. That's why they are higher. Now these other ones, if you begin observing them, they don't have hydrogen bonds. Okay, they don't have hydrogen bonds, so most of them are actually non-polar. Okay, these two are not non-polar, but then most of them are non-polar, so they are basically more dependent on the LDFs, which are dependent on the size of the molecules. That's why as you go down the group, because this is like on top, and then you are going down the group. So as you go down the group, you expect that the LDFs will actually begin to do what? To increase. Because if you check actually the next question, it's actually asking the factors that affect the London dispersion forces, which among which is the size of the molecule. Okay, so let's now summarize the answer here. Group 4. Explain the observed trend from group 4. So the group 4 molecules which are starting there, these are all non-polar, right? Okay, so these being non-polar, they exhibit or they show only London, or they possess only London dispersion forces, okay, which increase with the size or the molar mass. Okay, so leading to a gradual increase in the boiling point. So group 4 elements or group 4 molecules that are shown on this diagram, they are all non-polar, which exhibit or possess only the London dispersion forces or the van der Waals of attraction. So the London dispersion forces of attraction are dependent on the size. They increase with the size, and so since we're going down the group, the size is increasing, so that's why we can see that there is an increase in the boiling point. Okay, this is the smallest, that's bigger, the biggest. So the biggest has got more London dispersion forces, so therefore it requires a higher boiling point to break the forces. Now for group 6, what's happening there is there's some hydrogen bonding involved on the first part. Okay, so they exhibit hydrogen bonding. There's a hydrogen bonding in water, that's why it's on top there. and dipole to dipole forces in that guy. Okay, so possibly even in this in fact all these other ones have got dipole, right? Yeah, because of hydrogen, presence of hydrogen bonding. And then if you try to observe, this is group 6, and so group 6 with hydrogen will give us the dipole to dipole interactions. So the dipole to dipole forces exist in these others, and then there's hydrogen bonding in water. That's why water has got a higher boiling point compared to the others. And then there's also a presence of the London dispersion forces, which are of course dependent on the size. So in simple terms, the reason why it's like this is there's hydrogen bonding in water, okay, and then the dipole to dipole forces in the others. Okay, that's why the boiling point first of all reduces as you go down the group, because water has got hydrogen bonding. Then it begins to increase due to the effect of LDFs, which are dependent of course on the size. Okay, so I've explained. I hope you've gotten it. You should be able to explain now in your own words. Okay, so if you're still having challenges understanding the kind of forces that I've explained, please feel free to watch the first video under under this topic on the site, phase diagram, intermolecular forces. The first video is about 15 minutes long. I've explained the types of forces or the types of intermolecular forces in detail. Okay, so the London dispersion forces of course exist in all molecules, including the non-polar molecules. Now, what affects them? So I'm from mentioning what they actually affects them. So we said the size. So the molecular size, or the size of a molecule, in other terms, affects the London dispersion forces. The higher the size, the bigger the size, the higher or the stronger the London dispersion forces. Okay, that's number one. They are also affected by the shape of the molecule. So the ones that are actually stretchings or longer have more surface area for interaction than compact shapes. So longer flexible chains would imply stronger or more London dispersion forces because there is more room for interactions. Then the compacted ones, for example, if you go to the organic compounds, you find that we get to have aromatic compounds. Those ones tend to have less because there is less room for interactions. Then thirdly, the polarizability of the molecules also affect the London dispersion forces. So this just describes the ease with which electron crowds can be distorted. How easily can you distort the electron crowds? How easily can you move the electrons? So more polarizable molecules have got stronger dispersion forces. Okay. Question 4. What types of intermolecular forces exist between the following pairs? This requires greatly your attention. Okay. So hopefully you've watched the video. I've explained the different kinds of intermolecular forces of attraction that we have. That would be easy for you then to understand these. So it's important to be able to understand or distinguish the polar from non-polar, and also be able to identify the hydrogen bonding, and also be able to identify the ions and whatnot. So let's begin with the first one. If you look at the first one, are they polar or non-polar? Just a few tips here that can help you out. Whenever you see the hydrocarbons, these ones are non-polar. Okay. When you see presence of hydrogen and then you see it's attached to group 6, don't even hesitate. It's polar, meaning that if you see HCl, if you draw it like this, there is a presence of partial positive charge on the hydrogen and partial negative charge on the chlorine. So such compounds are what get to form the dipole to dipole interactions. Okay, then the ionic compounds like sodium chloride and this guy, for example, these ones that are charged, um, they tend to form ion to ion interactions. Then when you see the presence of hydrogen and nitrogen, hydrogen and oxygen, hydrogen and fluorine, these ones form hydrogen bonding in addition to the dipole to dipole interactions. Okay, so that has given you at least an idea of what to think about. So this guy is polar, that guy is polar. Okay, okay, so what do you say when they are polar? So polar implies we've got dipole to dipole interactions, and then they all have LDFs, right? So therefore between them we're going to definitely have dipole to dipole interactions and also LDFs. So just know that LDFs exist in all of them, so random dispersion forces. Okay, that's for the first one. For the second one, we've got chlorine. Chlorine is of course a non-metal. It's non-polar. There's no charge on chlorine, right? So these ones that are existing, they are natural form. There's no charge. Okay, so chlorine is a gas, so non-polar. Now this guy, carbon connected to bromine. Carbon is in group 4. Bromine, what group is bromine? So bromine is group 6, right? I'm just trying to counter check my periodic table. Yeah, but anyway, bromine is in group 6, so this is definitely non-polar as well. So both of them are non-polar. So when they're non-polar, the only forces that exist are definitely the London dispersion forces. Okay, then we move to the third one. Iodine as well is in the same group. So iodine is definitely not charged, it's non-polar. This guy, we can clearly see it's got a sign, so it's an ion. Okay, so an ion, when an ion begins to interact with a non-polar substance, it induces a charge on the non-polar substance. So those interactions, we get to call them the ion-induced dipole. Okay, in the similar manner, if you can have HCl, which is of course polar, which of course will form dipole interactions with itself, if it's to again interact, for example, with a non-polar methane like that, that would also induce, it would form what we would call dipole induced dipole. Okay, so that's basically what we can say there. So ion induced dipole is what we're going to have for C, because this ion will induce some charges on the non-polar iodine. Now for the last one, this guy, ammonia. Ammonia has got hydrogen bonds in it. Hydrogen bonds are dipole to dipole interactions, right? So this is hydrocarbon, which is non-polar. So equally this will induce some charge on that. So it's going to be a dipole induced dipole. Okay. And of course, all of them have London dispersion forces. Okay, so that's it to question 4. I hope you've gotten it. I hope you've understood how we've answered it. I'll move to question 5. Okay. Question 5 is based on phase diagram, and phase diagrams basically just show us how pressure, temperature affect these phases of a substance. Okay, So the way I usually like thinking of it is I draw a line that will cut all the three parts like this, and then we'll start from solid, liquid, and gas. So you know that, okay, on top is solid, liquid, and gas, right? So solid, liquid, gas. Okay, so this point is called the triple point. That's where all the three phases coexist. That point is called the supercritical point. Beyond that point, um, that's the highest point actually where we can have the presence of a liquid, right? So we understand. So now, what processes are occurring at Q? So I've said this is a point where all the three states, the three phases coexist. Okay. So now, it's actually safe for us to say that all this should be the six processes should be able to occur at that point. So which um, you begin thinking of solid, liquid, and gas. So from solid to liquid, for example, that's freezing. From liquid to solid, vaporization, and then condensation, which is gas to liquid. So condensation, sublimation, which is directly from solid to gas, deposition, which is gas to solid, okay, melting, which is solid to liquid. So you see that all these six processes can occur at that point. So it's safe for us to say that since all the three phases coexist, it's safe for us to say all the six processes, the ones that I recently listed, occur at the point Q. What name is given to point R? Point R, I say that's identified as the critical point. Okay, critical point, that's point R. Okay, then define the critical temperature. So I think just at that point R, if you draw a line down, that gives you the critical temperature. So that is the highest temperature at which a substance can exist as a liquid. The highest temperature at which a substance can exist as a liquid, regardless of the pressure. Okay. And then what name is given to a material at temperatures and pressures above those points of R? So supercritical fluid. Okay, you can't actually tell whether it's a liquid or whether it's a gas. You can't tell the difference. It's kind of difficult to distinguish, but it's a fluid. Okay, so that fluid is called the supercritical fluid. Okay, now move on to question 6. Question 6. The vapor pressure of a substance is 23 at 210 Kelvin. Calculate the vapor pressure at 415 K if the enthalpy of vaporization is 28,000 kilojoules per mole. Okay. So how do we answer this question? Okay. Then from this one, we'll move straightforward and answer question 7 and also question 8. Okay, so to access the solutions to all these questions, I would call upon you to sign up on our site where you're able to learn each topic from scratch, all the concepts explained to you from stoichiometry all the way up to organic chemistry, accessible at any time of your convenience on our site. In addition to that, you're also able to access quizzes that will assess your understanding of the concepts that you will get to learn, and also look at the tutorials and the past papers that are readily available for you. Okay, the link is in the description below. See you on the other side. Link to the full video is below as well.